I have to note that the Jesse Sharp going off Niagara Falls, I actually listened to the narrative, and actually it was a guy going off falls in Brazil who actually survived. Jesse Sharp was a guy who went off Niagara Falls and didn't was never found, so I presume he didn't survive in 1990. But I guess we don't have video of that, so correcting that for the record, I suppose. Not that it makes much difference. So today, as we get 4 minutes to go or so, the warm-up period. It's fine with the lights, right? You can see that just fine? Yeah. Oh, see, it even has narrative closed captions on it, so you can see what's going on. And so we've been talking about Bernoulli, and we've always assumed that we know these things like velocities, we can determine them somehow. And the question is, how do we do that? Of course, you could put a stick in a stream and time it as it goes down a set distance for open channel flow. I guess you could put particles in a plexiglass tube and look at how quickly they go as they get carried downstream, hopefully at the velocity of the current. But usually the easiest way to do it is a little bit like the pitot tube on a plane. And that is that you constrict flow somehow. And so a pitot tube constricts flow by having it destroy all the momentum of the flow at the tip of it. So the velocity goes from, the relative velocity of the air coming at it goes from a big number, the velocity of the plane, to zero as it hits it. And it measures also the pressure, ambient pressure in the atmosphere on the side of it. And from those two differences in pressures, all the velocity of one of them is destroyed and converted into pressure because they're at the same elevation. You can use that to calculate what the velocity is. And so it's exactly the same mechanism that's used in pipes. You have a constriction, so you change the flow rate with this disc that goes partway across it. You measure the two pressures on these yellow pipes that go up here at the constriction and downstream. And you have a differential pressure gauge. Differential pressure gauge is just a membrane that has two pressures on either side of the membrane. The membrane deforms. On this case, the high pressure would have been on the left-hand side. You calibrate that deformation with a pressure, and so you could calibrate it with a standing weight of water, right? Because you know the pressure that would be at the base of that water if you have a column. And then you know that that deformation means that pressure. And so if you can measure the pressure differential between upstream and downstream, you can, and you know the geometry of the constriction, you can get a measurement. So they mentioned at the beginning, it's based on Bernoulli, Daniel Bernoulli, and the other technique is a Venturi flume, where you constrict it. A Venturi flume is where the shape of the constriction, instead of being a plate that has a smaller hole in it than the pipe, is actually a graded closure, a bit like this. This isn't all of it. I'm sure they'll show us a true one where it just the waist of it necks down, and is a gradual change in velocity, or gradual change in cross-sectional area. So a gradual change in velocity. This is it here. So a Venturi flume would look like this, and you can get the most accurate readings of the velocity from that. So that's it. That's how you do it in. So we'll talk a little bit about that today. It follows right on from what we've talked about before, and that is that we need to use Bernoulli to get the v-squared terms on either side. And we also need, since we have those two terms that are unknown, we have to use continuity, which is the velocity times the cross-sectional area has to be constant along the pipe. V1 A1 equals V2 A2. So that's all it is. And so I'll see if they actually make me take this video down. I think in the past this has been a strike, a copyright strike. So I don't know whether it will be this time or not. And so sometimes they just say that if you want to leave it there, then the company has rights to get data, usage data from your posting. So it's only been a couple of cases where we've had something that it's been a strike. 3 strikes and you're out, I guess, if YouTube. So if you have 3 copyright strikes in a certain period of time, maybe in 3 months, then they kill your YouTube account. Not happened yet. Still waiting for it. So that's how you might make these measurements in a pipe. If you're out in the field and you want to know what the stream flow is in a little stream that's going across your plot of land that you're the engineer for, then a typical way is to put a weir across it. And so in other words, you dam it with a board. The board has a notch in it. The notch in it has an upstream head and a downstream elevation. And maybe either from the upstream and downstream elevations, or depending on the situation, from the upstream elevation relative to the bottom of this board, you can use essentially the equation of a free jet that we've already talked about to be able to figure out exactly what the flow rate is. And of course, for a river, you could also figure out other ways to do it. You could drop a stick into it and time its distance over a length, and do that perhaps at a number of different sections on the surface. I suppose those might be the fastest velocities in the river, because you could imagine that at the bed of the river, it's dragging along the base, and so it has some frictional resistance to get past. So that's what we'll talk about today. Okay. Any questions to deal with before we get going? I sent out a reminder. You should have got a reminder at midday on Wednesday to sign up, register for Monday and Wednesday, I think. Actually, no, I didn't. I only sent it to people who hadn't registered. So I'm able to do that. So make sure you're registered for Monday and Wednesday. Anything else come from that before we get going? Yeah, fine. You'll be just fine. So that is our plan for today. So we will do this. And this. So to recap, well, we spent a lot of time on, we did really two things. We talked about Bernoulli at the top here. We made the point that we have these 6 unknowns. If you have 2 unknowns in your equation rather than just 1, then you have to be able to link these velocities, and the way you do it is by continuity. So we're now, weeks 4 and 5, we're talking about Bernoulli. Week number 6, if I do it. Week number 6, we talk about conservation of mass. And so that's the one that will be online next week. And conservation of mass is that mass rate in equals mass rate out unless you get some accumulation. So it's no different from this. Week 7, we talk about conservation of momentum. And conservation of momentum is this. You remember that this equals ma equals f, right? This term is the ma term, the acceleration term. If you're accelerating a fluid because it's going from a velocity here to a different velocity here because it's squeezing through this gap in the stream tube, it's accelerating. So the velocity is changing. So the rate of change of momentum is what we're interested in. And so week 7 is Bernoulli equation, but written for more complex and general geometries. And then week 8 is conservation of energy. And conservation of energy is, well, thermodynamics. Don't delve into it too much, you'll be happy to know. But it's chemical energy that provides, you burn a fuel, it expands, it creates kinetic energy. It's how many of the things that we use work. Internal combustion engines, gas turbines, etc. And so we can use chemical energy, but we can also use it to look at losses. And so the losses that we look at will be frictional losses, because these use energy in a system which is otherwise conservative. There's no energy that's used in this. You go from a certain amount of energy upstream to the same amount of energy downstream, there's no loss. But if you have frictional losses, or if you put energy into the system through a pump, then you are adding energy into the system, and we need to know how to do with that. So that's what we talked about last time, and that's how it leads in. We did a couple of examples, kind of with a free jet. The equation turns out to be essentially the equation of a free jet, as we have this. We can look at the pressure that results when this velocity is destroyed as it hits this, and that allows us to do a free body diagram to see what power we need to be able to run one of these jet lev things. We did, somewhere we did the Scottish Flying Scotsman, to talk about that for a bicycle. And then we talked about solving for free jets and the fact that the streamline velocity we get is always a streamline velocity. It can just as easily come out of the side of the tank. It's still the velocity, but it's a streamline velocity. And that we can think of the water, it's no different from a body from your dynamics class that's falling. So as it falls from this particular location here, it falls at gravity at the same time it's moving horizontally. And so we can use that to say something about, for instance, how far it would go from the nozzle. So that's kind of what we talked about last time. So we didn't do that question. Maybe we'll come back to that if we do too much today. But let's talk about measurement, so flow measurements. So these are the things we'll talk about today. Flow measurements, these are the videos we just looked at in a pipe in an open channel. And then we'll talk about the limitations of Bernoulli. So when we talked about Bernoulli, we said it was for these 4 requirements: irrotational, no vortices, no turbulence, incompressible, no viscous losses, and steady state. And so we'll just talk about how those work. And we'll find out that actually we can be much more lax about it than those very stringent requirements. So for once, I'll use our notes to talk about what we're trying to understand. And that is, well, maybe I'll draw something. If you look at behaviors as you go from upstream to downstream with a pipe, and I can't resist just drawing something. And actually this is a useful diagram. From upstream to downstream to 2. We could look at what we can look at. Bless you. We can look at the elevation. So this is Z1. This is Z2. I can't remember whether we've done this pictorial representation of what's going on. This would be gamma. This would be some imaginary P2 over gamma. And this would be some imaginary V1 squared over 2G. So we know that these are the magnitudes of this. And we haven't talked about it yet, but we could imagine that if we're putting energy into the system with a pump, that what that represents is a pump head and head loss. They don't have to be equivalent. So if we go back to this, I'll come back to this. So these are the 2 extra terms that we have in Bernoulli that represents energy we're putting into the system and energy we're taking out of the system by the frictional losses as it goes along this pipe. And so what we will define is this EGL is an energy grade line. And one other thing we have is a hydraulic grade line, which is just the sum of the pressures and the elevations, not the velocities. In this particular case, we know that if this pipe has the same areas, upstream and downstream, then by definition, from continuity, the velocities have to be the same. The same velocity here as this. So these heights have to be the same. If these heights are the same, then this is Bernoulli without the losses, right? Over this. This is Bernie. Daniel's line. And if this is the same and the elevations of these 2, then that means that by default, this is horizontal, these 2 are the same heights, these 2 are the same elevations, so the pressure difference between upstream and downstream have to be the same. That's not true in real pipes because real pipes have frictional losses along the sides of them that use up the energy as heat and sound, perhaps. And therefore these terms come in here, that this is the pump head, not H1. This is the pump head that's added to it, and this is the pump loss that's destroyed as you go down here. And so we'll deal with that later. But all I want to make the point is that for now, we're thinking of Bernoulli with no losses, and therefore we're horizontal line. And so we can add these things up, and they will always look relative to this top line. Actually, I think this is actually the EGL. So forget about this down here. And so that's the principle of measuring these. So if you go along here, by definition, if you write Bernoulli to be the sum of these components, then if the velocity goes up at point 2, by definition, the elevation or the pressure have to change. If it's on a horizontal line through here for this streamline, then the only thing that can change is the pressure. And if we get a change in pressure, we can do it. So if you're flowing through at a small velocity, then you get a small dip in the pressure. If you have a big velocity, then potentially the pressure can drop. So if it goes below the vapor pressure of water, it'll cavitate. You'll get little bubbles forming. So if you look at submarines, military submarines, they have these huge propellers on them that look like the propellers on planes. And that is so that those propellers can go very slowly, because you know that on an airfoil, which is what a propeller is, the way that an airfoil works is you drop the pressure here by accelerating the fluid over the top. That provides a drop in pressure, which provides you lift by the change in pressure going down, right? So it sucks the thing up. So that's exactly what happens on the backside of a propeller. If it goes very fast, you'll get bubbles forming. When those bubbles collapse, they make a noise, and that's how you detect submarines going around the globe, by using hydrophone networks in the ocean, listening posts, basically. And so I'm sure that when the Titan sub, was that the one that went off the Grand Banks looking for the Titanic, when that exploded, I'm sure that was picked up by some hydrophones that probably weren't divulged. And so I'm guessing that someone knew about that much earlier than the 5 days before they figured out there was a sound as it went down in descent. That's, of course, a big bubble going, right? Meter by 3 meter bubble just imploding at one time. So flow rate measurements, we said that we use these flow meters. We constrict the flow either with a plate in the direction, a curved plate, or a venturi, which is a shallow narrowing of the orifice. The expression that we need to deal with is very simple. If we are horizontal, then we can assume that the elevations are the same. We can write Bernoulli in this way. I always like to write it in terms of the unit weights, but this is the other way that you can consistently write it. And of course, we have a velocity at 1 and a velocity at 2, which we don't know, but we'll be able to measure the pressures at these two locations. So to be able to constrain these velocities, we have to write conservation of mass. And so with these two equations, we can combine them to be able to get this. I won't go through the derivation. You just have to write either V1 or V2 in terms of the other one. You do it. You'd write V1 is equal to A2 over A1 V1. And then you throw it in here, and you only have V2 in this equation. And if you can figure out what the other two pressures are, then you can solve it. And so that means that you can get the flow rate, volume rate per unit time, as a result of the area at point 2, wherever that might be. If it's you can write it at either way, you just need to write it in the right way. So in this case, the constriction is 0.2. This pressure will be depressed because it's increasing in velocity, just like we've talked about here. And then if you use those in the right sign convention, this term on the bottom is just a consequence of linking the velocities upstream and downstream to each other through continuity. And so if you measure the differential pressure, you don't need to measure the absolute pressure at P1 and P2. Typically, you can measure the differential pressure much more accurately by this differential pressure gauge. So you have an upstream part, you have a downstream part. It's joined by a membrane. The membrane displaces, just as we saw in the movie. and you measure that displacement to get the relative pressure, and you can solve for the flow rate. So that's it. You need to know what the density of the fluid is that's flowing. Typically you know that, water or oil. You need to know the geometry of the constriction, and you need to know the pressures. And sometimes there might be some coefficient that goes on this if it's not an ideal Bernoulli no-loss system, because as you can see in these cases, if you have vortices developed behind it, then it's not really irrotational flow, so Bernoulli might not be so accurate, and so you might need to correct it in some way. And so going from quite a rude disturbance to a more gentle disturbance to a really gentle disturbance gives you better results with less correction. So how do you solve some of these problems? What do we have to do? So we'll talk about that today. We'll talk about open channel flows as well. Maybe we'll do an example. So how would you solve this? So what we did before, we solved Bernoulli, and we solved for pressures. So here we have Bernoulli, and we have a manometer equation as well. So if we want to solve this, what we could do is we could write Bernoulli for these 2 points. So we know that flow is coming from upstream, it's hitting this, and it's going around it, and then it's going downstream, like this. And so we know that this velocity here and this velocity here might be similar, I guess, except for there's this cross-sectional area which makes things a bit more complicated. And we also know that probably we can get the pressures between this point here and this point here by using this manometer. And if you think about it, the manometer is killing the velocity, so it's elevating the pressure. And the manifestation of that is that if you think about taking this U-tube and blowing on the upstream, you'd think that the gauge fluid would be horizontal. If you have a higher pressure on the upstream than downstream, you'd think that it would depress and go up. And so that's kind of what we'd expect to happen. So we can write Bernoulli between those 2 points. So 2 equations. I won't solve it, but I'll certainly write the equations that you need. And it's solved below, so you can follow that if you want, if you prefer. So that's our expression. What do we know? We don't know P1. Let me circle the things that we don't know with my nice circle tool. Love it. Z1 and Z2 are the same. They're not zero. Well, they could be 0, I guess, if we just put the datum through there. V1 squared is equal to 0. V2 squared, we'd like to know. And P2, we'd like to know. So we have one equation, we have 3 unknowns, and so we're going to want to constrain things in some way. And so one way to constrain it is that if we can write this in terms of P1 minus P2 over unit weight is equal to V2 squared over 2G. So that's going to come out of this. And so if we can do that, then we can define this relationship in terms of this. So we want to know what P1 and P2 are. And so our way to do that would be to assume that we know P1 and P2 and just go through the manometer equation. So I would write that, if you remember, P1. So we start off at P1. We go up some amount, which is L. So if I get this right, you remember I got it wrong last time. Going up in a swimming pool, you reduce pressure, so you subtract. So L times unit weight of water in the pipe, oil, I guess, oil. Gets to this point, we can go across this because it's the same fluid. We get across to this point here. We go up again, so we subtract H times gamma gauge fluid to get to this point here. And then we go down this amount here. This amount here is H plus L by this definition. So we add H plus L multiplied through by gamma oil, and that equals P2. Should have probably done it the other way. I could make these all negative, I guess. And then I can, bless you, and I can add P2, so I can subtract it from the other side. No, actually I don't need to. Why did I do that? I can make my life better. So I can write this, I can subtract P2, P1 to get rid of this. And then I can make this negative P1 minus P2 by just having plus L gamma 0 plus H gamma G minus H plus L gamma O. I guess we'd lose this and this. Do we lose the yeah, and so we just have H minus H, sorry, we have H gamma G minus gamma water equals this. I said I didn't want to do it, but I guess I've ended up doing it. And so we have this, and we can equate that with this. So we have pressures defined in terms of an elevation, which we need to know, and unit weights, which we know because we know that the unit weight of oil is equal to 0.83 times the unit weight of water, or the gauge fluid, I guess this was, right? This is the gauge fluid. No. This is oil. And so we have that, and so we can solve. So we can solve for the magnitude of this as a function of h. If we're given h, which we have, which is 4 inches, we can solve. So that's it. So, don't overcomplicate things. All we've done is we've written Bernoulli. We've seen that we have 3 terms that we don't know. 2 of those 3 terms we can write as the difference between each other, which should be manifest in this height. You can rationalize that just by thinking of it. So the difference in these pressures you can define by h. And so if somehow we can define the difference in those pressures in terms of this behavior, you can solve for v. The difference in these pressures you get from the manometer equation, and then you substitute them all together, and you end up getting the velocity out of it, which I haven't calculated. And if you know the velocity at point 2, then the flow rate at point 2 is just equal to the velocity at 2 times the cross-sectional area at 2. And so you don't have to deal with this little shrinking in the velocity in the areas that occur here. Nowhere do those differences occur. Okay? That's it. So if you are on the surface, then you can use exactly the same deal. You can look at a weir. This is an undershot weir rather than overshot weir. An overshot was the one that we looked at in the video in the run-up to the class. We can do exactly the same thing. This is kind of a free jet. If this was infinitely big reservoir, if Z1 was much bigger than Z2, then we could probably write that V1 is equal to 0. but if not, we can't. So otherwise, we can write Bernoulli for this again. P1 over gamma plus Z1. It's written down below, so you don't necessarily have to write this. Equals P2 over gamma plus Z2 plus V1 squared, V2 squared rather, over 2G. And so depending on the circumstances, if the velocities aren't zero, then you can't get rid of this one. So if V1 isn't zero, then you can also write that the width of the dam, which is B, times Z1, which is the area. Right. I'm just burning to use this. A. This at times V1 is equal to B times Z2 times V2. Don't care about the widths if it's a unit flow, and these are the constraints. And so that's exactly what you have here, and these of course are equal to the volumetric flow rate, which is actually what you might want to determine. And not so dissimilar from this case here was that you have turning up on the bottom of this the ratio of two areas or the ratio of two lengths. We could also do it for the free jet if we didn't assume that the tank above the free jet was infinitely wide and the velocity at the surface was not zero. We'd also end up with a ratio of the areas of the tank at the top and the jet. But that's a characteristic of all of these problems, is that you end up with this correction term on the base, which is due to the fact that the upstream velocity is not equal zero. So you'd end up with a relationship for this if you write it at point 1. And of course, point 1 and point 2 are on the top of the flow. So both of these are atmospherics. So you can get rid of these two expressions as zeros, as below. They're different elevations. So the essence of this problem is that this elevation here is different from this. And so if you have a stream gauge upstream which measures the height relative to the downstream height, that's all you need to make your flow rate measurement. So this flow rate measurement just comes from solving these two expressions by writing V1, by linking V1 and V2. So it would be it'd be V2, right? This must be V2. So this must be V2 is equal to V1 Z1 over Z2, that's all. This goes somehow into this. Perhaps I've done it backwards, and you solve for this, either one or the other. And so you get these as a function of the elevations, upstream and downstream, and you can solve for the flow rate that goes through it. You could also, if you wanted to, the other streamline here, you could write it as point 1 here, and you could write it as point 2 here. But if you did that, you just have an extra pressure equation to contend with, because this pressure here would be equal to P2 is equal to rho G Z2, right? Just from what we've talked about fluid statics. You know, we talked about Bernoulli, fluids going across curves, into curves. When you do that, if you're going into a curve, this becomes flatter and the pressure increases, just as you feel the pressure increases in your seat as you go in a dip in a car. And if you go over the lip of a curve, then the pressure in the cup that you have is reduced. That's the same. If it's going horizontally straight, then it's just swimming pool pressure distribution, or you'd expect it to be. And there might be some corrections you could apply. If you imagine a different kind of weir, an overshoot weir, where the water goes over the top, you have a similar behavior. You could write this is a streamline, obviously, that goes down here. Well, it's not a straight line. This is a streamline here that goes down here. So you could write it as point 1 and point 2 if you wanted to. You could write it here as point 1 and you don't know that this, you could assume it would do this, but you don't quite know that. Or you could write it at a generic point, which is at some depth, and a generic point here, and assume that kind of goes through here. And so in these weirs, you typically get separation here. So if you wanted to survive in a hydraulic, you'd be able to breathe if you're stuck in this location here, because it's air. It'd just be a tunnel, like surfing a big wave. And so this is almost, you could imagine this is a free jet. It's not very different from us having the bucket on a surface, where the bucket looks like this, and water comes out of here. And we know that in this particular case, if this is Z, then V2 is equal to is it GZ? 2GZ, yeah. This term here. And so you know that for a free jet, if it was this, kind of looks like this, right? It's going horizontally. It happens not to be a completely uniform distribution, because you can imagine that where it hits this wall at the top, it gets retarded by the fact that it's dragging on here. And, well, I don't know whether it would be this or whether you'd think that it might look like this in reality as it goes up to the surface, because there's nothing impeding it at the top. So it's not necessarily a uniform distribution like we're assuming for the free jet is here, but it should be something similar to it. So if you assume that it might be similar to a free jet, we can write that the velocity at point 2 is proportional to 2gh as we measure this height. Proportional means we need to have a calibration coefficient in it. So we can equate it to it if we know what this calibration coefficient is just by experimentally. If you want to get the volume, then we can multiply the cross-sectional area, some cross-sectional area, by this height, which is this. This is the area of flow. Just as before, B is into the page. And so that's this, not divided by, but equal to A. And so you just multiply by the total height of the system. So the total height would be the depth of this particular location here, just like it is here. And everything else is calibrated out. And so you can calibrate it. You can realize that this height here might be similar to this height here once you calibrate it with this coefficient. And so you can take that magnitude outside, because this is h to the half and h to the 2 over 2, h to the 3 over 2, and everything works out. So that's it. And you can do all kinds of mental gymnastics to figure out exactly what that might be. I won't bore you with that to know what those are, because you can just use them as standard results. So that's that. What else do you want to talk about? I guess the last things, yeah. So we'll talk about actually go back to what we talked about before. We talked about grade lines and what Bernoulli means if we draw it in this way. So this is quite a useful way to think about Bernoulli, that this grade line here is really the fact that Bernoulli is constant. Of course, if this pipe was constricted in some way, if it did this, then what would we expect to happen? Certainly Z1 and Z2 are the same. This velocity here, I suppose, since the area is bigger, has to be less than this velocity here. And so we could imagine that the grade line would actually be swapped, so it might look like this. This is wider, so this true velocity would be this. This true velocity would be this. I know it's getting a bit messy on here. We know that Bernoulli upstream and downstream have to be the same, so this line is anchored, so that can't move. We know that the elevations of the upstream and downstream point can't change. And so the mere fact that this velocity has to be smaller than this velocity means that this pressure upstream has to be larger than this pressure downstream. So that's useful. And it's actually no different from what we talked about in terms of this, right? If it accelerates through here, and it is accelerating, it's accelerating in space, it's going at this velocity, and it's going at this velocity plus some here, so as it goes downstream, it's accelerating. So not only is the change in velocity changing with time, so if you're anchored to this particle and going downstream, then the velocity is increasing as you go downstream. So the velocity increases with time. I won't draw that, right? At this time here, it's 1 meter a second. At this location here, it's 2 meters a second. So if you're in a capsule, a pig, that's, as they call them, that's going down a pipeline, if you want to move fluids down pipelines, and they're different fluids, then you put the oil down, and then you put a pig, which is just a block on the pipeline. You send that down with another fluid behind it. When it gets to its destination, you pull the pig out, and then you just route the flows into different locations. So if you're going down in a capsule, then I've lost my train of thought why I was saying this, then you would experience different pressures as you go down here. And so because the velocities are different as you go down here, the velocity of that pig experiences a change in velocity with time as you go downstream. So that's an acceleration for you as you're in that pig. You can also write this, as you recall, as dv dt times dx. And again, this is what we've called convective acceleration. This is t, right? So this dx dt is equal to velocity. So this term is equal to rate of change of velocity in space multiplied by the velocity. This is that same as that acceleration. So this means that if you're at this point here, the velocity is changing as you move linearly along here. Clearly it is, because it's 1 meter a second here and 2 meters a second here. So this has to be finite, and this would be just the velocity here. And this is exactly the expression we used before, so that we saw that with a free jet, we did the calculation, right? To say that if you have a free jet that's coming out of here, and this is the distance for the free jet, probably over belaboring this point, then the velocity here is accelerating. So the velocity here is equal to 2gz, as we know. And we know that the acceleration is equal to the velocity times dv dz. And we did it last time. We differentiated this, and we find indeed that the acceleration is just g. It might be minus g. No, it'd be g. Minus g, I think, because it's going downwards. G is positive as an acceleration, but in our coordinate system it's negative. Yeah, when you differentiate the z, you get a negative sign as a result of that. So anyway, so that's a useful way to think about these things. So the other way to think about it is in terms of this other diagram that you have here. Don't want to give you whiplash. Exactly the same expression that we've done before. I guess I was wrong. Yeah, that's right. The hydraulic grade line is just the one that goes on top of the elevation, the pressure. But we can draw this for a more complicated geometry. We haven't put in the pump amounts. This is our energy grade line. This is what we've called our EGL, or energy line. And if we look at this behavior as we're upstream, we have a hydraulic grade line we say before that the hydraulic head is equal to the pressure over the unit weight plus the elevation. We do these because all of you who are dealing with fluid flows in the ground, environmental systems engineers, petroleum engineers, energy engineers for geothermal as well, I guess, and mining engineers a little bit for groundwater. When we solve the equations for flow in porous media, we don't care about the velocity squared term. We assume that v squared over 2g is equal to 0. So if you're flowing in porous media, typically the velocity is very small. Typically the changes in velocity are quite small, and therefore we neglect this term. And what's much larger are frictional losses in the system. You don't care about that now. So we define a thing which is hydraulic head. And we call that uppercase H, which is given by the hydraulic grade line in this particular case. And so if you look at it upstream, there's 0 velocity, then v squared over 2g is equal to 0. If you're at the surface here, the pressure is equal to 0, and therefore the elevation of this point, h, is equal to z1. Interestingly enough, if you do it at point 1 here, then h would be equal to P1 over gamma plus z1. And in this case, z1 is equal to 0, if this is the datum. And so all you have done is replace the potential energy due to its elevation by pressure energy due to its depression below that surface. You've just exchanged one for another. As it comes out of this nozzle, now all of a sudden it has a velocity. So the velocity at this point is non-zero, so you have some amount. The elevation of this point is non-zero because you know that. So these are the two things that you know. Well, you know it's non-zero velocity and non-zero elevation. And so the difference between those must be the pressure. And then as you go to this point here, you know again that this must be the elevation. You know here it's coming out into the atmosphere. The atmosphere we're taking as gauge pressure, so that has to be 0, which is this. And so this must be the full velocity making up the energy grade line. So we can understand those things in terms of those terms. So think about Bernoulli in terms of that. This fact that this is horizontal means that there's no loss of energy in the system, which is a requirement of Bernoulli. The other useful thing in terms of a thought exercise in this is to take this system where you have this constricting nozzle, and I guess you also know, you'd expect that since this is constricted, the velocity times area here and the velocity times area have to be the same. This area is smaller, and so we know that V2 A2 equals V3 A3. So you know that if A1 goes down, then V3 has to go up. So you also know that this has to be larger. So the other thought exercise that's useful is to think of it in this term. So instead of having, say, a pipe that comes out of this that was the same area as you go downstream, if that was the case, then you'd know that everything was constant. Then you could look at pulling the pipe down and pushing the pipe up. And so what do we know here? Here we know that if we know the velocity of the pipe, if its cross-sectional area is the same, the velocities are the same at all of these points. So I suppose V equals constant in the pipe. You know its elevation here, and so you know this for sure. If you know this velocity in the pipe, then you know it has to be anchored at this point and goes down to this. And so the subtraction of those would give you this pressure here. So now, if you take the pipe and move it up, then again, you know the velocity here is the same. You know the elevation of here is elevated. And so if you want to get down, so the proper way to move between those would now be to go down from here to this line. And this line would be P over unit weight, which would be less than atmospheric pressure. And then you go up from here to get the velocity squared term. And so if you're going up to get to this point, that means that this pressure here is lower than the pressure here, just as the pressure here has to be larger than as it comes out of here. So this is the same as it's reducing in pressure. So if you bring this pressure up high enough above this, then I guess, well, no, you can bring this high enough so this pressure could actually be less than the vapor pressure. So one way to get air out of your system, if you're doing experiments and you don't want bubbles of air to come into your experiment, is to put a vacuum on the water. So air will dissolve in water under normal atmospheric pressure because it's being pushed in there by 101 kPa. And so if you want to get that dissolved air out of the system, you put it in a vacuum. So you put it in a container and put a vacuum on it, or you could just run it along a pipe horizontally. And if you take that pipe so that it's 30 feet up, about 10 meters, then because 10 meters of head is 101 kPa, then it goes through the vapor pressure of water. And so what it would do is it tries to flow like a siphon, right? It has to flow in a siphon. If it goes through absolute zero pressure, it will cavitate, it will bring the air out of the water, and it will collect it in a little jar up here, comes back down, it's de-aired water, and you can use it in your experiment. So that's one way to do it. And, well, all these interesting facts, kind of has some relevance and stuff. So that's our way of looking at Bernoulli. Think of it as an energy grade line which is horizontal, and that upstream and downstream they have to match each other. Bernoulli is useful. We can use it to do these rate measurements for flow rates in pipes and flow rates in weirs by using Bernoulli and using continuity equation to link the two areas upstream and downstream by specifically assuming that the upstream velocity is not zero. Of course, as opposed to the free jet where we anchored it at zero. And then we just have to worry about the other things that we said. We said incompressible fluid, irrotational, no vortices, no viscosity, and steady state. How strict are those requirements? Well, incompressibility. We use Bernoulli all the time for air around the wings of planes to look at lift, and it actually works quite well. You might have to sometimes use the compressibility in certain cases. We'll do a question with a gas cylinder that's decapitated and what velocity of air comes out of that as one of our examples later on in this class. Certainly you have to account for the fact that it's feeding that flow by the expansion of the air, which is a gas and very compressible. But Bernoulli works quite well. So we can actually use it for gases, and we do use it for gases. Steady flow, well, we've already solved that one, right? We need to choose our frame of reference so it's steady. So if we're doing a submarine, we know that from the Flying Scotsman, we have to take a picture of the Flying Scotsman and be attached to the bicycle as it's moving along, or looking out onto the wing from the window as it's moving along, so that the picture of the air flowing over the wing is exactly the same as time 1 second, as 10 seconds, as 100 seconds in the frame of reference. So we can absolutely do that by making it steady by just choosing our frame of reference to do that. So for the submarine, we wouldn't sit ourselves at a static location and watch the submarine go past, because that is changing the flow every single frame of our video. We attach ourselves to the submarine, and an example for those flows, and so those are two. It actually works well for compressible flows. We'll use it. It acts just well for non-steady state, so long as we make our frame of reference so we force it to be steady state. If there are vortices, we may not be able to use it so well, but we've already alluded to the fact that in these Venturi flumes, even if you have a relatively rough transition, by putting a plate in here rather than a Venturi transition, Ben, you can still use Bernoulli to get the behavior upstream and downstream. And what else was there? Irrotational, incompressible, steady state. Was there a fourth one? There was, but I can't remember what it is. We can use it for that one as well. So anyway, so that's all I've got for you. Any questions for today? Don't forget that we don't get together next week. I'll send the thing out at midnight. Should have registered for your slot at Pollock on Monday and Wednesday. If you hadn't already registered, I sent out another reminder on Wednesday. So if you didn't receive that, then you're probably registered. Happy hunting. Yeah, it's all in your control. You have good skills. You have a good idea of what it is. And yeah, show your best. Good luck on it.